Number 3, we've got an initial value problem given here. We want to solve this differential equation and then solve for y explicitly. So looking at this one, I can see I can factor that x out, and so this will be separable because I can write this as dy dx equals x. So factoring it all the way out of that fraction, and I've got a y squared plus 1. And so that's separable. I got the y's and the x's separated. And so I'm going to go ahead and separate it, leave my dy on this side. I'll have to multiply by the reciprocal of this, which will put a y over y squared plus 1 on that side with the dy. And then I've got x dx on this side. And now I integrate both sides with respect to the variable that I'm looking at. And so the right-hand side is easy enough. It's just going to be x squared over 2 plus a constant. Over here, I will need to use a u substitution for the denominator. Du is 2y dy, and so that y dy is going to disappear as 1/2 du. So my differential equation, what I've got is the integral. I put a u in for that denominator, and then like I said, the y dy is going to get replaced by 1/2 du. And on the right hand side, well, we'll do this one in just a second. So now this one's set up. We're going to end up with 1/2 natural log absolute value of u. And the other side, the right hand side, is going to be x squared over 2 plus a constant. Okay, I'm going to go ahead and calculate that constant now by using this initial condition. I know that I'm supposed to get 1 for y when I plug in 0 for x. So don't need that. Plug in, get a 1 for y. Well, I guess I got to go back to y first, so let's do that. Sorry about that. Natural log absolute value y squared plus 1. Here's my substitution. Okay, that equals x squared over 2 plus a constant. So now I'll plug it in. I'll have 1/2 natural log absolute value, get a 1 for y. So that y is 1 squared plus 1 when I plug in 0 for x. Okay, so this is going to be natural log of 2. 1/2 natural log of 2 is my constant. So I'll plug back in here. I get 1/2 natural log absolute. The absolute value is unnecessary now because this is obviously positive. Y squared plus 1 equals x squared over 2 plus 1/2 natural log of 2. I can multiply through by 2. It'll clear out all my halves. So this will give me natural log y squared plus 1 equals x squared plus natural log of 2. And then I'll take e of both sides, giving me y squared plus 1 equals e to the x squared plus natural log of 2. You can actually simplify e to the natural log of 2. You can write this as a product on the right hand side, e to the x squared, e to the natural log of 2, and that's 2. So this is 2 e to the x squared. And then I'll subtract 1, so I get y squared equals 2 e to the x squared minus 1, and then I'll take the square root of both sides. So I do have to put the plus or minus since I don't know for sure what I've got here, whether it's positive or negative. So anyway, this would be my final explicitly solved for y solution to this equation. Number 4, we've got this differential equation and we want to find the equilibrium values, or also called the critical points, and we know all we need to do there is set dx dt equal to 0, and what we'll get is x equals 0, 2, and 4. So there are your critical points. And then we want to draw a phase diagram to determine the stability of each of these equilibrium values. So remember, what we do is we think of a sign chart, and I'll put my factors over here. They were x, I'll scroll back up, 2 minus x and x minus 4. So x, 2 minus x, and x minus 4. And then I need to know what happens with my derivative x prime. Put each of your critical points in here. Well, there were 0, 2, and 4. and then determine the signs. Well, these are linear factors. X is 0 here, so it's negative on this side, positive on this side. You can check that by just plugging in a value on either side of this particular line. This one is 0 here, this is the second factor. This one turns out to be positive on this side and negative on this side. In other words, when you plug a number in bigger than 2, you're going to get a negative. And then this last one is 0 here, and it turns out to be negative on the left and positive on the right. Just check by plugging in some x's. So the result of multiplying these three things together is I'll get a I'll get a positive, two negatives and a positive, then a negative, positive, negative. And I know that means that it's increasing, decreasing, increasing, decreasing. So that's our sign chart, and from that we can get our phase diagram. And so there's my x-axis and my t-axis. I'm going to put my equilibrium values on here. So there's one at 0. I'll make it a different color. So there's an equilibrium value here at 0. And then there's one at 2. And then there's one at 4. And what I've just determined here is that if I pick something below t equals, these are my x's. If I pick, it's increasing for t's less than 0. Sorry, x is less than 0, right? So I'm doing this in terms of x. So it's increasing, which means they're going to go this way. Decreasing between 0 and 2, between x equals 0 and 2. And then increasing between 2 and 4, so that'll go that way. And then decreasing some bigger than 4. So looking at that, I can see that this equilibrium is stable, because regardless of where I am, it's going to push me back into it if I come off that equilibrium. This one is unstable because it's getting pushed away from. And that last one here at the bottom is stable.